Okay, so this is going to be called assessing the model or the performance of the model. So we've done that already, but we want to do that in the context of a regression problem. And I'm using that word in a more general sense. We talked about classification is when the output variable is categorical, and regression is when the output variable is numeric. So I'm using it in that sense. So if we have a numeric output variable, we really haven't discussed how to measure the error. We have done it for classification. We've seen, like when we had the iris data and we saw something like it did 96%, we had 96% accuracy. So we saw that before. And what did that mean? We can recall that we have the confusion matrix, and I think I can't remember which is on top, but let's say the prediction is on the top and the actual is across here. Then, for example, if we have 10 instances in here, that means, and this is class A and this is class B, so this is when we only have two classes, that would mean that it was predicted to be class A and it was actually class A. And suppose we had 90 here, that would mean that it was predicted to be class B and it was actually class B. So those would not be errors. On the other hand, if we had something like 20 here, so that would mean those would be errors, and that would be what? It was predicted to be class B, but it was actually class A. And let's suppose we had another 80 here. So that would mean we'd have 100 errors here, because this is also an error. So out of, I think we have a total of 200. So the average, the overall accuracy would be 50% in this case for this particular confusion matrix. Anyway, we have talked about how to do this, how to get the accuracy. But when we're talking about regression, it doesn't make sense anymore, because what would we do? Let's suppose we were predicting a stock price. So the stock price, let's say, is anywhere between $0 and $150. So what are we going to do? We could have like the predicted price could be 0, could be 1, could be 2, could be 3, all the way up to 150, and then we'd also have to have 150 rows. That would, first of all, basically be impossible, but that wouldn't even do it, because it could be, this could be like 0.8 or 80 cents, right? So then we'd have to have another, at 0.8, we'd have to have another line. We couldn't do it. We couldn't have enough lines. It's basically kind of like an infinite number of lines from 0 to 150, or an infinite number of divisions between 0 and 150, and the same thing here. So it just doesn't make sense to talk about, to use this kind of scheme to measure the error. However, think about if you have, let's say, something like this. Let's have it like that. And let's say you're trying to predict the price, and this is like day 1 and day 2 and day 3 and day 4 and day 5. So the actual price, let's put some color here. Let's say we should say the actual price is going to be, what color? Well, let's use blue. Okay, the actual price is going to be blue. So we had a price here, then we had a price here, then we had a price here. Then the price started to come back up. It started to go here, and here, here, here. Okay, so suppose that was it. Now, suppose our prediction, suppose we use a line as a model. In other words, that would be called linear regression. So what color should I use? I'll use something. Let's try this one. No, let's try. For the model, we should use a color. Well, we'll use green. Or let's try this green instead. Okay, and let's say the model was going to be linear, so we could use a line through it. we want to fit a line, or we want to have a linear model, maybe we'll use this to get our model. So then maybe it would look like this. Okay. So then, when we talked about this, then we could measure the error like this. Let's use red for the error, but maybe not this red. Let's try this red. Okay. Then we could talk about the error. Maybe I'll use this to do it. As being the distance. Oh, this is, oh, sorry, that was red. I don't want red. I want that, so that's green. Then I want to go here, then I want red. Okay, here's red. Okay, so the error might be like this. We talked about, no, that did not work. Okay, let me undo that. Okay, let me just try and draw it. So this would be the error. This is how far away the prediction is from the actual value. The actual is the blue, and the prediction is the height of the green. So there's some error there. You know, maybe this is perfect. It's unlikely, but let's suppose that was perfect. And then here's another error, and here's another error, and here's another error. So this is we can talk about. This is kind of the error of the model. Now in the talk that we're going to continue with today, we're going to say that these dots are only, maybe in this example of the time series, this isn't quite as clear, but let's suppose instead this was, let's change suppose this is not time anymore, but this is the size of a house, in square meters, for example, or square feet, and this is the price, the selling price of that house. So then here when the size was here, we have a certain that house. Each of these dots stands for a house, and that house sold for a certain price here. And then this size here we had another house which was this size, and it sold for something like here. And then we had another house here, and it sold for something like this. Right? That's about the height here, and so on. So what we're going to say though is a little bit more involved, and we're going to say that these. So how many houses do we have in this picture? 1, 2, 3, 4, 5, 6, 7, 8, 9. So that is certainly not all houses in the world, right? So we're going to say that this set of data is just a sample or a subset from what we call in statistics the whole population of houses, or a sample from, or a subset from all possible houses. So this is only a subset of that. Okay, of course, we only have whatever 10 dots here out of their millions and billions of houses on the market. So one point we're going to make later is that this green, suppose we used these dots to come up with this green line. Well, that's not the real so-called, even if we're going to assume that there's a linear relationship, we don't really expect that this green line is going to give it. Even though this green line might be the so-called line of best fit for these dots, but the real data, the set is all possible houses are going to be all over the place, and the best fit for all of those dots is probably not going to be this. So we say actually that this green line is just an estimate of the true model, because we don't have all possible data. So let's write that as well. So the green model is just an estimate, I'll have to write here, estimate of what we call the true relationship, or the true model. But for now, let's just ignore that and just talk about how are we going to measure the accuracy of this model related as compared to these dots. So later we're going to adjust our thinking a little bit because of this, what I wrote here in blue here. But right now we can just say, what's the error involved in using this green for these blue dots? So let's label the dots, and I hope I'll use the right notation here. So I think we talked about this. This one is like x1, because this is x1, and comma. Now, the question is, should I use f of x1, or should I use something else? And we are going to use something else. We're going to use that. And this height here, what are we going to say, or what are we going to say the coordinates of this dot? So this dot, maybe I should have made that green. Anyway, I'll just leave it the way it is. So that is going to have what coordinates? So that's also going to have the same x1 coordinate, but the green line, we're going to call it, we'll usually denote our model, or maybe at least right now, we're going to denote our model by f of x. So that's our model. Oops. F of x. Okay, so if this is f of x, then what's the height of this? It's f. Let me use black again. F of x1. Okay, that should be an x1 here. Okay, so that's the height of this, and the height of this we denote as y. Now, I think we also mentioned at one point that we will use y as the height of the actual data, so that's what I did here, and we'll use y hat as the estimated height. In other words, I'm saying that this is f of x1. In other words, the estimated height, or the height predicted by the model, will denote that if we want to use y instead of f of x1, if we want to use the letter y, we'll use y hat to distinguish it from this dot, which we're calling having height or y coordinate of just y. Okay, so what is the order? I'm sorry, what is the error? So what is the error involved? What is the error? It is the distance between these two. So we could call it, we called this y, and we called this f of x1, or y hat. So I could write it as y minus y hat. That's the error. Or if you want to write it the other way, you'd say y minus f of x1, either way. Now I guess we should call this y1, and this y hat 1, and this also y1. Okay, anyway, that's the error here. And then what's the error of the next one? Well, this one, can't really see it. Let's say x3. What's the error for x3? What color should I use there? For that, I should use this x3. So what's the error for x? So error for x3 is going to be what? So let's call this error for x1, or error 1, which we might also call epsilon 1. And the error for x3, or we might call it error 3, is what? So that's going to be y3, which is where? That's the coordinate of this point, the blue dot, minus the predicted height, which is here, which we could call y hat 3. And then we could have, this would be, again, y3 minus f of x3. We could use this notation like this. We could use this. We could call it error 3. We could call it epsilon 3. We could call it whatever we want. Okay, so we're going to be using notations like this. So then we have all of the errors, and then we want to add them all up. Now, some of them will be positive. So like this one is y1. This is y1. And this is y hat 1. So that's y1 minus y hat. So that's a positive error. This, I guess, is the way I wrote it. This will be positive, and this will be negative, and this will be negative, and negative, and so on. So anyway, we're going to sum all of these up. So if you want to write it with this symbol, we could say we're going to sum up all the EI. Or if you want to write it with the error symbol or the error word, you could say we're going to sum up the errors, I. Or if you want to write it this way, you could say we're going to sum up yi minus y hat I. And if you wanted to write it the last way, you could write it like this. We're going to sum up yi minus f of xi. So however you write it, that's going to be, we could do that for the error. Now the problem with doing it this way though, or the problem with doing this and calling that the total error, maybe total error, we could do that, but you might see that we're going to kind of get a lot of cancellation. And we may, or typically we will get complete cancellation. That is, it will be 0. The error will end up being 0. But that seems like not really acceptable to say the error of this green line is 0, right? I don't think we want to, that's not very interesting or useful. Somehow our measure of the errors is not correct. It's not right. It doesn't reflect what we can see right here. So we want to adjust our method of calculating the error. So we don't want to call the total error this. Okay, so this is not good. Let's not do that. So what we do is instead, well, we could do at least two things that are sometimes done. One is we could do this. Now, in that case, all of these are going to be positive, or we could put the absolute value here, put the absolute value here, put the absolute value here. In that case, they're all going to be positive, and this is not going to be 0. So that's one solution, and that's a good solution. And that has a name. That's called what? It's called the mean. Well, I forgot one part, but okay, let me do one more thing. We don't really want to just do this, though, because this will just keep getting bigger and bigger the more points we have in our data set. So if we have 10 points, we'll say the error for the model is one thing. If I have 100 points, this is just going to be much bigger because they're going to have a lot more terms there. So we don't really want that. We want to take the average error. So we divide by the number of points. So we could use that, and that is often used. And that is called the mean. Okay, so mean because we did the average. Absolute, because we took the absolute value, error. So it's called the mean absolute error. Now we have another choice, which seems less attractive, but it's actually the one that's used more often. And that is, instead of taking the absolute value, we could do this. We could square it. We're still going to get rid of that cancellation because everything's still going to be positive. Each one of these terms is still going to be positive. So we are going to get rid of that cancellation, although it seems like a strange thing to do, to square it. But that turns out to be more typical than this. It doesn't mean that you can't use this, but this is also another way to do it. So, and of course we want to divide by n again, and that has a name, and that's called the mean squared, not surprisingly, error. Okay, so that's the mean squared error, or this is the mean squared error, and this is the mean absolute error, and you could use either one of them. Now, in this case, what does y stand for again? Y stands for the price, right? Y stands for the price. So this is going to be some, for example, when we calculate this, when we calculate that, it's going to be y1, which is the actual selling price, minus the predicted selling price. So that's a price minus the price. Maybe the actual price was $1 million, and the predicted selling price was $700,000. So the difference is $300,000. So this is going to be in dollars, this error. And when we sum it up, it's also going to be dollars, right? But when we do this, if we end up squaring like this, then this is going to be dollars times dollars. So this is going to give us back dollars squared, which is kind of a weird unit, and we don't really want to work with dollars squared. And the other problem is that this is going to be quite huge because we square everything. So what usually is done at the end is to take the square root of that. So you do this over n and then take the square root. So that must have a different name than this, and that is called the root mean squared error. Okay, and then then we don't want to write everything out. So this one they call MA. Usually another word for error is deviation, because this is a deviation of the. We can think of this as the the deviation of the real from the predicted, or vice versa, the deviation of the predicted from the real, or whatever. So instead of error, sometimes we could call this deviation. And then when we write this, we call it the M mean squared. Oh, sorry, this one up here. Let's do this one. This is the mean absolute deviation. So it's called MAD, mean absolute deviation. Maybe it's also called MAE, but I don't think so, actually. This is usually what you see, the mean absolute deviation. Whatever it is, it's just this. It's just this. Just using the absolute value. And this one is M. They don't use deviation here for some reason, I guess because this looks easier, MSE. And then this one is the RMSE, okay, because it's the root, square root. So to review, if we're talking about a classification problem, we know how to measure the error. We did it with this confusion matrix, and we got, for example, here it's 50%. Okay, but when we're talking about numeric values, this doesn't really work. So you can't measure the error with some kind of infinitely divisible confusion matrix or something like that. And the only way you could do it is basically create intervals, but that's sort of moving away from numeric and actually moving to that would be binning this variable, and or discretizing this variable, and then you're really going back to a classification problem. So if you don't want to go to a classification version of this, you just want to stay with the numeric, then you have to come up with something else. And we did. We came up with something. We said these red. Now, actually, I think the truth of the matter is that this came first because regression is much older than classification, or I believe. So this was around before the confusion matrix, anybody considered a confusion matrix. So this concept of error precedes this concept of error, but it doesn't matter anyway. The point is that if you have numeric, we're going to choose from either the MAD or the RMSE to measure the performance of our model. How good is this model in relation to the data? And this can help us to choose different models. So we could use the typical one we're going to use is the RSME. So let's say we're going to use that. So we could figure out the RMSE of this, and then we could do something else. So let's suppose I tried to put basically the same data there. Let's suppose we had the same data. So we could say, okay, we just used a model, I'll write it in black. We just used a linear model, which means we just wrote something like y equals mx plus b, some line, right? Every line has this kind of equation. We usually don't use m and b. We'll usually call it a1 x to the first plus a0. So we usually, instead of writing m, we call it a1, and instead of writing b, we call it a0. But whatever we call it, this is a line. We just used a linear model. But we might say, okay, I want to get a little more advanced or a little more flexible model. And we might say, or a little slightly more complex model. And we'd say, let's use a model like this, a 2x squared, so we're allowing x squared into the model, plus a 1x plus a 0. So that's a more complex model than this. This kind of model is a subset of this, because if a2 is 0, then we get this, but here we allow a2 not just to be there, could be 0, but it could be many other things. So the set of models contained in here, this is a subset of the set of models contained in here. So anyway, suppose we're allowing this kind of model, then we're going to say we're allowing like a quadratic fit to this. So now maybe, I just drew this in. I don't know if this is a real, this is clearly not a real parabola, but maybe we could fit some kind of parabola to this data. And now we could look at the error and see, and maybe if we consider the error in this case, and if we consider for example, the RMSE, the root mean squared error, maybe it will be smaller. And that will give us a reason to say, oh, this model is better than the linear model. So once we decide on a measure for the model, we can we can choose between models. We can say one model is better than another. Now, one more thing. These, let's call them a color, say here, this and this, or this and this, this and this and this. These are called parameters for the model. So what that means, or the way we use that word, is we have the data, we have the blue. Maybe I shouldn't use blue for the word parameters, but anyway, we have the data, and then we try to fit a curve to that data. Now, there are many different curves that we could come up with, even if we're going to use a parabola. For example, a2 could be 1, and a1 could be 3, and a0 could be 4, something like that. There are all these numbers could be all different, and we're going to get a different parabola each time we choose the different coefficients. So the coefficients are called parameters, and depending on the parameters that we choose, we're going to get a different green curve and also different errors. So we say often that we're trying to choose the parameters that will give the best fit given the data. So we want to choose the parameters which optimize the model. So when we use that word parameter, like in this case, we're just talking about the coefficients. And in general, that's true. We're not always stuck with this. This is a polynomial, right? I'm sure you've heard that word before. This is a polynomial, right? And this is also actually a polynomial. And we can have higher order polynomials. For example, we could have y equals let's say 4, x to the 4th, plus a3, x to the 3rd, and so on. You know what I'm doing, all the way down to the end, which was a0. So we could do that. So we could have higher order polynomials, but we're not stuck with just these. Maybe something else fits better. Maybe there's some y equals e to the x or something, or maybe there's a parameter here, like let's call it a1, and even a parameter up here, let's call it a2. Anyway, but there's some kind of exponential curve that fits this. Now it doesn't really look like it for here, but maybe there's some other curves that we could come up with that are good. Maybe some sort of form of a sine function might be better. Who knows? This is just arbitrary, so it doesn't even make sense. But there could be all kinds of models, and the models all will have parameters within them. Like you might have, something like this: a1 sine a2 x, and then you want to choose the a1 and the a2, which will give you the best fit for this data. So we say we want to choose the parameters that will give us the best model or the best fit.